This video attempts to provide a mental model of how variables work in Python. Before getting into how variables work in Python, let's quickly see how it works in many other languages like C or Golang. When you create a new variable and initialize it with a value using the assignment operator equal to, memory is allocated in that function's stack frame to hold that value. The size of the memory allocation depends on the data type of the variable. For example, an integer may take 4 bytes, a float may take 8 bytes. In short, you can think of a variable as a container holding the value. The type of the value, whether it is an int or float, or string, is associated with the variable. When you assign a new value to an existing variable, the new value replaces the old value in the same memory location. You can also create a new variable by assigning an existing variable of the same type. Then a different memory is allocated for the new variable, and the data is copied from the memory location of the first variable. Now let's see how similar operations work in Python. You don't need to specify the data type when creating a variable. Everything is an object in Python. When you assign some value to a variable, a new object is created in the heap memory. Whenever I say Python, I mean CPython, that is, the reference Python interpreter written in C language. This is the most popular Python distribution. The PyObject represents the base structure for all Python objects. In the interpreter code, this PyObject is defined as a C struct. We will use this conceptual view in the remaining part of the video. We are interested in these fields: the type information, reference count, and the actual value. Once created, these objects do not move around in memory, that is, they have a fixed size and memory address. The variable name x is a reference to this object. Since x points to the object, its reference count becomes 1. When a new value is assigned to the variable x, a new object is created at a different memory address, and the reference is updated to point to the new object. At this point, the reference count of the new object becomes 1, and that of the old object becomes 0. Python's memory manager periodically cleans such objects with 0 reference counts. This process is called garbage collection. Notice that the type information is not associated with the variable. It is stored in the object. You can reuse the same variable name to reference different types like integers, strings, etc. This is why Python is said to be a dynamically typed language. Dynamic typing means that the runtime objects or values have a type, as opposed to static typing, where variables have a type. As seen previously, since the variable binding got changed, the reference counts get updated, and the garbage collector removes the unused objects. This helps in ensuring the overall memory usage of our application remains low. When the new variable is created by assigning an existing variable, Python doesn't create a new object. The new variable will be another reference to the same object. Note that at this point, the reference count field of the object becomes 2. Some people say Python doesn't have variables, and it has named bindings. If you think of variables as a container holding value, variables in Python are like label stickers on a container. When you delete a variable, the actual object is not removed. Only the reference is removed, and the reference count field of the object is decrement. When all the references are deleted or go out of scope, the reference count becomes 0, and the object is garbage collected. Till now, we only discussed basic immutable objects like integers. They are immutable because you cannot change their internal state once they are created. Next, we will see container data types like lists, which can hold other data types. Lists can hold multiple values, and their internal state can be changed by adding or removing elements. Instead of the PyObject, the basic structure for container type objects is the PyVarObject. The PyVarObject is just a PyObject with an additional size field. The size field is used to store the number of elements that the container object holds. The value field will be a pointer to the memory location of the storage array where actual elements are stored. Notice that the elements are not directly stored in this array. Instead, only pointers to the elements are stored. For array indexing to work, each element in the array must have the same size. The pointer to any type of object, no matter if it's a string, integer, or dictionary, will have the same size. This is why you can store different types of objects in a list in Python. On a 64-bit system, the size of the pointer is 64 bits or 8 bytes. Same as before, actual objects are created somewhere in the heap memory, and they all will have a reference count of 1. Since x is a reference to the list object, its reference count also will be 1. When you create a new variable by assigning an existing object, the new variable will be another reference to the same object, and the reference count of the list object becomes 2. When elements are appended to the list, new objects are created in memory, and pointers to them are appended to the backing array. Also, the size field of the list object is increment. When you print the elements of the list using both x and y, you will see all elements even though the append was done to y. I'm using f strings here within the print function. If you write a variable equal to an f strings, it will be replaced with a variable name equal to the value of the variable. Note that the backing array has a fixed capacity, which is basically the contiguous memory allocated for it. When you keep on adding elements to the array, at some point the array becomes full. Then Python allocates new memory, usually twice the size of the existing array, and moves items to the new array. The internal value pointer is then updated to point to the start of this new array, and the memory allocated for the old array is released. An important thing to notice here is that the list object, that is the address of the PyVarObject, never changes. Only the backing storage array is moved around in memory. Similarly, when copying elements to the new array, only the pointers are copied. Actual objects never move. This has another advantage that such copy operations are cheap in terms of memory since pointers are of small size, no matter the size of the actual object they point to. Now, let's see what happens in memory when you write code like this. From now on, we won't be drawing the entire PyObject on the screen to represent an object. None is used to represent empty values or null pointers in Python. Like everything else, none is also an object. From what we have seen so far, when the first statement is executed, a none object is created in memory, and x will be a reference to it. Similarly, when the second statement is executed, we expect another none object to be created and y to be a reference to it. However, it doesn't happen that way. A new none object is not created. Instead, y will be another reference to the existing none object. You can verify this using the built-in id function. In CPython, it returns the memory address of the object. As you can see, both x and y have the same address since they are references to the same object. This is called interning or reusing objects. In the start, Python preloads or caches a few of the most commonly used objects, so that it doesn't have to recreate them when needed. Integers in the inclusive range -5 to 256 are also interned. So new objects are not created every time you use them. If you use a number not in this range, for example, 257, a new object is created every time you initialize a variable. In the case of strings, strings that look like function names are interned. That's why the first two are not interned since they contain the space character. Note that in the case of integers and strings, this is an implementation detail, and it may change in some future versions of Python. It's possible to intern custom strings using the intern function from the sys module, but I haven't seen any use of it in normal application code. Python has two ways to check the equality of two objects, the double equal to operator, and the built-in is keyword. Let's see the difference between them. This is the representation of a list object with 3 elements in memory. The elements 1, 2, and 3 are not stored directly in the array. Only pointers to those objects are stored in the array. But for simplicity, I will just show them directly inside the array. The built-in identity function returns the unique ID of an object. In CPython implementation, the address of the object is used as the unique ID for objects. Assume there is another list with the same elements. Here, if you check the equality of x and y using double equal to the operator, you will get true. But if you use is, you will get false. This is because the double equal to operator compares both list objects element by element. The is keyword compares their addresses. If x and y were references to the same object, is will return true. Is keyword should be used to check if a variable is none, since only one none object is ever created by the Python interpreter during the lifetime of your program. Next, let's understand how variables are passed to functions. Here, we define a list with elements 1, 2, and 3. This list is passed as an argument to the function. Within the function, we will assign a new list to the input parameter. Then we check if the value of our original list was modified outside the function. A function has a separate scope. Function arguments are passed by assignment in Python. So what we saw earlier in this video about assigning an existing variable to a new variable applies here also. The assignment creates a new reference to the original object. So the my_list and nums will point to the same list object. Within the function, when a new list is assigned to my_list, a new list object is created and my_list will point to this new list. When the function returns, the my_list goes out of scope. And the newly created list will also be removed by the memory manager because there are no more references to it. This means assigning a new value within the function won't change our original variable outside the function. Suppose if we actually wanted to change the original list from within the function, we need to use the methods defined on the object. Here 10 is appended to the original list through the reference available within the function. Even when the function and my_list variable go out of scope, the changes persist. Python allows you to define a default value for a parameter when defining a function. Here, if the user calls the function add2 to list without any arguments, the value of my_list will be an empty list. Then we append 2 to this list and return a reference to this list. As expected, when you call the function for the first time, you get a list with a single element. When you call the function second time, it returns a list with 2 elements instead of 1. This is probably not what you wanted. Remember, everything is an object in Python, even functions. The function is an object of the function class, and the function object is created at some memory address. The function objects have a $defaults attribute, which stores the default values as a tuple. Consider this as the function object created in memory. It has a my_list attribute. The function object gets created when Python executes the function definition, that is, the def statement. As part of this, Python evaluates the default arguments for the function. In our case, an empty list object is created somewhere in the memory and a reference to it is stored in the my_list attribute of the function object. Note that the function body is not evaluated at this point, it only happens when you call the function. Like any other object, the function name add2 to list will be a reference to this function object. When we call the function for the first time, 2 is added to the default list. And our variable first becomes a reference to this list. The same thing happens again when you call the function. 2 is again appended to the default list, and the variable second becomes another reference to it. Note that I'm using a list here, but this behavior is the same if you use any mutable container types like a dictionary or set or something else. Even though the way it works is the same, you won't have any unexpected behaviors if you use an immutable object like integer or string as default parameters, because there is no way to mutate their internal state. A better approach is to use none as the default value for mutable objects. Then within the function body, check if it is none, if so, create a new one. You can either use the if statement, or just use the OR operator as shown in the commented code. Let's look into a special behavior of the += operator. The same applies for other augmented arithmetic assignment operators like -=, multiply =, etc. Here we have a 2-element list object. Both x and x_copy are references to this object. You can confirm this by checking the identity of both x and y. Next, we will append another list with 2 elements 3 and 4 to our list using the plus operator. Python always evaluates the right-hand side first. It creates a copy of our list, then appends the new list to it. Since we are assigning the result back to x, x becomes a reference to this new list. The original list stays unchanged and we can still access it through the variable x_copy. Let's reset the memory representations to the original state. Like many other languages, we can replace this operation with the augmented assignment operator plus equals to. The value of x becomes the same as before, but how it does is different this time. New elements are appended to the end of the existing list. The address of x is not changed, and both x and x_copy will see the new value. The reason for this behavior is that, when Python sees the plus equal to operator, it calls the dunderiad method of the object. When you call a method of an object, Python automatically passes self as the first argument. This self is another reference to the same object. The name self is just a convention, you can use any other name. Inside the method, this self reference will be used to mutate the internal state of the object. Also, the dunderiad method returns the self, which gets assigned back to x itself. Thus, x stays as a reference to the original object itself. Now let's see a situation where understanding the augmented assignment operators is useful. Here, we are declaring a tuple with two elements. Remember that the round brackets are not necessary for declaring a tuple. What makes it a tuple is the comma. You can verify this using the built-in type function. As you know, tuples are immutable. You cannot change their value once they are created. An exception is raised when you try to modify a tuple. In the next example, the second element of our tuple is a list with elements 2 and 3. As expected, if we try to assign a new list, an exception is raised. However, we can still modify the list using its methods. Let's see why it works even when the tuples are immutable. When the first statement is executed, memory is allocated for the tuple, and it will contain pointers to the actual objects. In our case, an integer object and a list object. When we try to assign a new list to the tuple, Python is trying to update the pointer or memory address stored in the tuple object with that of the new list. This raises an exception since the tuple is immutable. When we use the append method, only the list object is modified, not the tuple. Let's see an example with the augmented assignment operator plus equal to. Here, when we try to extend the list with plus equal to, an exception is raised. But if we look at the contents of the list, it's actually modified. Why does this happen? As we have seen, plus equal to operator gets converted to dunderiad, which extends the existing list. After the right-hand side is evaluated, Python tries to assign the address back into the tuple. Note that the address is not changed, it is trying to assign the same address value itself, which is effectively a no operation, but this assignment causes the exception. As you can see, since the right-hand side is evaluated first, the list gets modified. This is why, even though it's kind of an unexpected error, this behavior is part of Python's data model.